So this is the formula for calculating the rate of change. You take a look at the difference in your output value, so you can think of that as some y sub 2 minus y sub 1, and divide it by the change in your input value, some x sub 2 minus x sub 1. We use this delta symbol here in mathematics to represent change, so sometimes you might see change in y, or delta y over delta x. That just means change in the y values divided by the change in the x values. Okay, let's take a look at a few examples. So here we have a function given to us as a table of values, and the function represents the smartphone sales and feature phone sales measured in millions of units over time. So you can think of time, the year, as your input value. So think of that as the x values. And then the sales, these are our output values. So we have two different functions here. We have a function for smartphone sales and then a function for feature phone sales. And we're going to take a look at the average rate of change between 2010 and 2012 for each type of phone. So let's go ahead and do that. So I'll write down here smartphones. Let's start with that. So whenever you have a table of values, I tell students it might be easier to pull out the data and write it as an ordered pair. So here you would write it as some x comma y. And so 2010 would be your first point, and that would be comma 301. And we don't have to put all the zeros. We know our unit is in millions of units. So this is our first point for that function. And then the second point would be the point 2012. So we can call this x sub 2 and 661 million smartphones. So that's my y sub 2. So now that I have that, I can go ahead and calculate the average rate of change over this particular interval. So using the formula, I would do y sub 2 minus y sub 1, so 661 minus 301, and divide that by 2012 minus 2010. And that gives us, I'm going to go ahead and simplify it here, 180 million smartphones per year. Okay, so we can see for smartphones, over that interval from 2010 and 2012, their sales increased, and I know it increased because this rate of change is positive, and it increased at a rate of 180 million phones per year. Now for the featured phones, so feature phone, I don't even know what a feature phone is, but for the same year, so we're looking at over the same interval, those coordinates or those points are 2010, comma 1079. Again, so you can think of this as x sub 1, y sub 1. And in 2012, their sales were 914 million units. So that's x sub 2 and y sub 2. And then now let's calculate the average rate of change using the same formula. So 914 minus 1079. Divide that by 2012 minus 2010. And if we go ahead and simplify this, this gives us negative 82.5 million phones per year. So for the feature phones, we can see that because the average rate of change is negative, that means that their sales decreased over the same interval. And it kind of makes sense because if smartphones are becoming more popular and their sales are increasing, then that probably could be a reason for why the feature phone sales are decreasing. And then the numerical value here, 180 and 82.5, tells us how fast the rate of change is, okay? So here we're looking at the same example as the previous one, but we want to take a look at the average rate of change between 2012 and 2013. And instead of doing it for both types of phones, let's just focus on the smartphone right now. So recall that the average rate of change in sales for their smartphone between 2010 and 2012 was, what was it, 180 million smartphones per year. And so that was the rate of change between 2010 and 2012. But now we want to take a look at what the rate of change is between 2012 and 2013. So again, you can write the points down as an ordered pair. To 2012, 661, and 2013 was 968 million iPhones. Now let's go ahead and calculate this average rate of change. and see what that gives us. So 968 minus 661 divided by 2013 minus 2012. So that gives us 307 million smartphones per year. So it looks like their sales are still increasing over time, but if we compare it to their sales between 2010 and 2012, we can see that the rate of change in the more recent years is much greater. So their sales are increasing, but at a faster rate. So 307 versus 180 million per year. Let's take a look at another example. Here we want to calculate the average rate of change over a specific interval, but the function is given to us as a graph. So in a situation like this, if I want to calculate the average rate of change for this function f, so f is that blue curve, okay, that's the function, between x equals 5.2 and x equals 6.1, then I need to know, so let's write down here, the average rate of change is the change in the output or the change in the y values divided by the change in the input or the change in the x values. So sometimes it's easier to use this formula if we can pick out our 2 points. So here we're focusing on when x is 5.2, so that's this point here. And we can write that, so this is the point, 5.2, comma, and its corresponding y value is 2.9. So you can think of that first point as some x sub 1, y sub 1. And we want to know what's the rate of change between that point and when x is 6.1. So 6.1 is right there. So 6.1, its corresponding output value is 4.9. So we can think of this as x sub 2, comma, y sub 2. And then now we can just put it into the formula. So the change in y is 4.9 minus 2.9, and we want to divide that by the change in x, 6.1 minus 5.2. Okay, so this gives us 2 over 0.9. I'm going to use a different color here, green. So in green, this distance here, right, in green represents the change in y, which is 2 units. Right, so that's how far away the points are from each other. I'll call this point A and point B. That's how far away the 2 points are from each other in the vertical direction. But in the horizontal direction, so I'll use red here, we can see that this distance here in red, that's the change in x. So how far away are the 2 points in the x direction? And that is 0.9 units. So if I simplify this, it gives me a rate of change of 2.22. And here I don't really have any units, so I can't say units per units because we don't have any context. It's just x and y. We don't really know what x and y stands for. Okay. In this last example, we want to calculate the average rate of change over a given interval, but the function is given to us as a formula. So here, anytime you have a formula and you want to calculate the average rate of change over a specific interval, you have to evaluate the function at the given input value so that you can get your 2 points, okay? So here's the lidocaine function again, the amount of lidocaine left in the bloodstream over time, where time is measured in minutes. And I went ahead and did the math for you, but you could also double check this by putting it into your calculator. So I want to calculate the average rate of change between 24.5 minutes and 100 minutes. So how is the rate of lidocaine left in the bloodstream, right? What is that rate of change over this time interval? So if we go ahead and substitute t into the equation and calculate a of 24.5 minutes, so you substitute that in for wherever t is in the function, it turns out that that's 25.6 milligrams. And then when we substitute in 100 minutes, so wherever you see t in the formula, substitute 100 into the formula, and it will give you a corresponding value of 15.4 milligrams. So now I have my 2 points, and you can write it out as 2 points instead of written like this. So this is the points, or these are the points written in function notation. And we can rewrite the function notation as an ordered pair. So 24.5, you can think of that as t sub 1, comma, 25.6 milligrams, and that would be a sub 1. And then the other point is 100 minutes, so you can think of that as t sub 2, comma, 15.4 milligrams, so that would be a sub 2. So now when it comes to calculating the average rate of change, the average rate of change over this interval would be the change in your A values divided by the change in time. Okay, so here that would be 15.4 minus 25.6 divided by 100 minus 24.5. And I actually did not work this out ahead of time, so let me take out my calculator and do this with you. So 15.4 minus 25.6 gives me negative 10.2. And then 100 minus 24.5 is 75.5. And then let's divide that numerator, 10.2, and divide that by 75.5. That gives me negative 0.135. And the unit here would be milligrams per minute, because time is measured in minutes per minute. So because this average rate of change is negative, this is telling me that between 24.5 minutes to 100 minutes, the amount of lidocaine is decreasing, right? It's leaving the bloodstream at a rate of 0.135 milligrams per minute. So in the next slide here, I'll show you what that rate of change looks like on the graph of this beautiful function, or this equation, okay? So here we have a graph of that lidocaine function. So this equation here, it's graphed for us over time measured in minutes. So we can see what the function looks like between 0 minutes all the way past 250 minutes. But if we focus in on 24.5 minutes, so 24.5 minutes is this point right here, 24.5 minutes, and 100 minutes, which is this point here, we can see that, I'll call this point A and point B, we can see that between point A and point B, so over this interval, the function, and I'll use green here, you can see the function is decreasing. So that's why the average rate of change was negative. And then the rate of decrease, so the rate of decrease was that point, I already forgot what we got, 0.135 milligrams per minute. So that tells you how slow the lidocaine is leaving the bloodstream. It's leaving it at a rate of approximately 0.135 milligrams per minute.